This is a very basic Olympiad problem for 6th graders who just learned fractions. So let's solve it. What should we do first? We should look for a pattern because mathematics is all about patterns. And if we look closely at the denominators of these fractions, then we can see that each denominator is a product of two sequential numbers. 20 is 4 times 5, 30 is 5 times 6, 42 is 6 times 7, and so on. And what is remarkable about all these denominators? The thing is that we have two sequential numbers, so their difference is 1, which means that we can rewrite the first fraction here not just as 1 over 4 times 5, but as 5 minus 4 over 4 times 5, which is now equal to 5 over 4 times 5 minus 4 over 4 times 5. And if we reduce these fractions, then we have 1/4 minus 1/5. And we can do that to every fraction here. So 1 over 5 times 6 is equal to 6 minus 5 over 5 times 6, which is equal to 5 over 5 times 6 minus 6 over 5 times 6. And if we reduce these fractions, then we have 1/5 minus 1/6. And again, it works for each fraction. Let's, for example, take 1 over 72. This is equal to 1 over 8 times 9, which is equal to 9 minus 8 over 8 times 9, which is equal to 9 over 8 times 9 minus 8 over 8 times 9, which is equal to, if we reduce these fractions, 1/8 minus 1/9. So if we do that to every fraction in this sum, we have 1/4 minus 1/5, which is the first fraction, plus 1/5 minus 1/6, which is the second fraction, this one and this one. Then plus 1/6 minus 1/7, which is the third fraction, then 1/7 minus 1/8, and so on. So this is 1 over 72, and this is 1 over 19. And that helps us a lot because these two fractions add up to 0. These two fractions add up to 0. These two fractions add up to 0, as well as these two and these two fractions. So we basically have 1/4 plus a bunch of zeros minus 1/10, which is now just a difference of two fractions, and we can calculate that. That is equal to 10 minus 4 over 40, or 6 over 40, or 3 over 20. And that's the answer. Now, that idea actually works not only for sequential numbers like 4, 5, 6, 7, 8, and so on. It works for any arithmetic sequence. Here's a similar task. If we have to evaluate 1 over 5 times 8 plus 1 over 8 times 11 plus 1 over 11 times 14 plus 1 over 14 times 17. So I've got these numbers from an arithmetic sequence: 5, 8, 11, 14, 17, which is just a sequence with a difference of 3. So 5 plus 3 is 8, plus 3, 11, plus 3, 14, and so on. Now, is 1 over 5 times 8 equal to 1/5 minus 1/8? So is this equality true? Well, if you remember the previous problem, then the answer is no, they're not equal, because in the previous problem, two numbers multiplying at the denominator were sequential, so their difference was equal to 1. 5 minus 4, for example, was equal to 1. That's why we had 1 in the numerator. Whereas in that case, we have two numbers with a difference of 3 and still 1 in the numerator. So this should be equal to 3 over 5 times 8. Let's prove that. Actually, we just can calculate that. 1/5 minus 1/8. Let's find the common denominator. So we multiply this by 8 and this by 5, and we have 8 minus 5 over 5 times 8, which is equal to 3 over 5 times 8. So this fraction isn't actually the difference between these two fractions. But if I multiply and divide it by 3, then nothing changes for that problem. So if I do that, then I have 3 over 5 times 8 plus 3 over 8 times 11 plus 3 over 11 times 14 plus 3 over 14 times 17, which is multiplied by 1/3. So I multiplied that 3 by every fraction, and what I have left there is 1/3, which is here. And now every fraction here is a difference between two fractions. For example, this fraction is a difference between 1/5 and 1/8. So I have 1/5 minus 1/8 plus here I have 1/8 minus 1/11, because this is just a similar fraction. Here I have 1/11 minus 1/14, and here finally 1/14 minus 1/17, and this is all multiplied by 1/3. And now these two fractions add up to 0, that is 0 as well, and here we have 0. So the result is 1/5 minus 1/17 times 1/3, which is now equal to 17 minus 5 over 5 times 17 times 1/3, which is 4 over 5 times 17, or 4/85. So this is our problem generalized, and what we need to do is just to notice some pattern here, which is in that case an arithmetic sequence. And when we notice that, we have to represent each fraction as a difference of two fractions. So thank you for watching this video. I hope you learned something new, and if you did, then watch another one.